Hi everybody, it's Dr. Chabot, and in this video we are going to work through an example using Ohm's law to analyze a circuit with multiple resistors. So this is not the example that we're working through, this is just a second example that is provided, just like with the capacitor video on the same idea. And so I want to walk through the basic steps that are listed here. We'll apply them to a different example, work through that one in detail, and then you also have this one as another reference. So if we look at what we have here, we have similar steps to what we had for capacitance. We're going to do this windy logic table again. First, we want to find the total equivalent resistance. That's always what we're going to do. And then we're going to draw the table, and we're going to start with the total circuit, just like we did before. We're going to use that total circuit, and then we're going to use that in order to go ahead and look at the last step of a circuit and map either V total or I total onto it. So the process is actually very similar to what we did with capacitors combined in a circuit as well. And then we continue to work backwards in this windy path through the table. What that looks like when it's been worked out is shown here. And again, the key results are going to be that we can find all of the individual values of the resistor. We can find their individual voltage drops and their individual currents by navigating our way through this table. The top line, just as before, is always going to be equal to our equivalent total circuit values. So those are kind of the fundamental results that we get from that. All right, so let's go ahead and work through an example of our own. So here's the example that we'll work through. We can note that in this circuit that R1 is in series with R2, and that is in parallel with R3, which is in series with R4. So if we look at the equivalent resistances, I'm going to again want to keep track of these individual values. R12 is in parallel with R34. So I can find those individual values. Notice that R12 is in series, so R12 is simply going to be equal to 3 ohms plus 7 ohms. So that's going to be equal to 10 ohms. I want to keep that value. R34 is going to be equal to 10 plus 30, and so then that one is going to be equal to 40 ohms. And so if I have 10 ohms in parallel, so if I draw my kind of second to last equivalent circuit, I would end up with down here R12, and it is in parallel with R34. And that's going to be an important thing because I'm going to note that my last step was a parallel step, and we'll come back to that, but I'll make that note as I'm doing this equivalent resistance. Note that this last step is parallel. That'll be important later. And so if I do this, then I can say, well, 1 over the total REQ, which is going to be 1, 2, 3, 4, is then going to be 1 over R12 plus 1 over R34. So I end up with 1 over 10 plus 1 over 40. And so then that's going to end up being 4 over 40 plus 1 over 40. So I get 5 over 40. And so then I can flip that and I see that REQ will be equal to 8 ohms. So now I'm ready to make my table, right? Because I have my equivalent resistance and now I can go ahead and set up the table for this. So let me go ahead and do that. Okay, so here's the table that I've set up. You notice that I have, just as with capacitors, I have that the total circuit is at the top, on the top line, and then I have my individual resistors, right? These are my individual resistors, and then I have my intermediate equivalent resistances. So those are my intermediate REQs that are going to be used in this circuit. I have put in the values that we've calculated already. So with the equivalent resistance and the intermediate equivalent resistances, those were all calculated in step 1 when we found the equivalent resistance of the circuit. And then we can say, here that we want to use now Ohm's law and our logic to wind our way through this puzzle. So the first thing we want to do is look at the total circuit. We have this equation, delta V equals IR, and note that it can be arranged so that I equals delta V over R. And so the first thing I want to do is complete this top row. I can see that then this is going to be 10/8, and that will have units of amps because I have regular ohms and regular volts in this problem. And again, that 10 volts was just a given 10 volts stated in the problem. The individual resistors were given. We calculated that equivalent resistance, and that now is giving us our total current through the circuit. And so now is where we want to note that the last step that we did was a parallel step, right? And so if it's a parallel step, that was the R12 in parallel with R34. That means that they are going to have the same voltage drop across them, and their voltage drop is going to be equal to the voltage drop across the battery. So again, remember with this table, it's that one of these two values is going to map onto one of our equivalent resistance values, and it's a matter of which one. And the answer to that is always hidden in that last step, whether it was a series or a parallel step. So in this case, we are going to map our voltage, and so that's going to be that it's the voltage total that maps. And then that's going to be equal to R12 and R34. So we map that voltage on down to those other values. Once I have 2 out of the 3 values in a row, I'm now able to go ahead and calculate the missing one. So I'm going to calculate this from delta V over R. So I get 10 over 10. So I just get 1 amp here. And then over here, I get 10 over 40. So I get 1/4 of an amp through that one. And so then those are going to be my two branches. And we can do a quick check here. That 1 plus 1/4 equals 10/8, which is in fact true, because 10/8 is going to be 1 plus 2/8, which is 1 plus 2/4. So that's our total current split, and we didn't lose any. So that's a nice quick check. And then now that we have calculated these values, once you calculate a value in an intermediate step, those are going to map on to something else. So we want to then note that if R12, if we deconstruct R12 and we just have R1 and R2, remember that the current through each one is equal, and it's equal to the equivalent. So that current is going to map. So R12 is going to get mapped onto R1 and R2. R34, for the same reasons, will get mapped onto R3 and R4. And then once again, we can now kind of finish off this table by calculating these other values. So we can see that delta V is just simply going to be equal to IR. So I end up with 3 volts there and 7 volts there. We can note that they add to 10 volts as they should. Over here, I get 10/4 and I get 30/4. And that's going to tell us how much voltage, how much of the buckets each of those resistors get. What we note is that the higher resistor, so the bigger the resistor, then the more voltage drop it gets when it's in series, right? So when you're going to have the electrons walking through with their little buckets. And I will, just for fun, draw my little electron guy again with his bucket. Then one way, a little cartoon model, way to understand it, is he has some amount of, again, energy in his bucket, and he has to divide it up between the resistors. And so if the resistors are going to be a tiny little resistor, and then a big giant resistor, he's going to look and say, okay, that big resistor definitely needs more energy. So he's going to get more energy, and he's going to get less energy. And that's just going to be in proportion to their relative resistances. And that is, again, when they are in series with each other, so that they have to share that energy that's coming through. Okay, so I hope this example helped. And let's go ahead and look back at the first example that I put up to see what the differences are there. So here's the original example that I put up, just as another example that you can look through and work through. And what we're going to see here is, if we look at this circuit and we were going to describe it, I would say here that I have 1 is in series with 2, that's going to be in parallel with 3, and then that whole combination is in series with 4. And so my last step, essentially, my last intermediate step is a series step. And so unlike the one we just did, where the last step was a parallel step, what that's going to do is it's going to change what gets mapped. So that means that it's going to be the I total that will map onto the intermediate steps for R1, 2, 3, and R4. And so if we look at the table for that, we can see that that's exactly what's happened here. So in this worked portion of the example, we can see that then it's going to be our I total that then gets mapped onto R4 and R1, 2, 3. And that starts this windy logic puzzle through the table. So a lot of times it's just that first starting step where you're picking between mapping the voltage or the current, and you have to decide, was that last step series or parallel? And so I have these two different examples where we worked through one where the last step was parallel, and then this example is one where it was series. So hopefully this gives you everything you need to navigate using Ohm's law to analyze our resistive circuits.